how we could use deep learning in the form of convolutional neural networks to do image classification. And we saw some really well-known architectures. And today we will see how people have started to use those ideas and those architectures to apply them to object detection systems. And we will see how these systems have evolved over time. So specifically, we'll talk about some differences between detection and classification, some evaluation data sets and some metrics as a background knowledge. And then we will see the two major paradigms in object detection, the region-based methods and single-shot methods. So classification with deep convolutional neural networks, as we saw in the previous class, basically revolved around ImageNet. So people were trying to develop methods to get a higher accuracy on ImageNet. But we have reached a point where people are just pushing for 1 to 2% improvement. It's not clear how that improvement can lead to actual benefit. So there has been a shift from classification methods to more elaborate tasks like segmentation, detection, and captioning. And we're going to see in this class detection, in the future in other classes also segmentation. So for the purpose of object detection, what we want to do is to repurpose an existing convolutional neural network that was developed for image classification to predict, rather than predict a label, to predict not only a label that specifies one object in the image, but rather predict bounding boxes that enclose different objects, and also predict the class of each of these objects. So we're going to see how to change the standard image classification convolutional network so that it can do detection. So as you can see in this image, there are many challenges facing object detection systems. We need to account for multiple instances from multiple classes that appear in the image, and we also may have overlaps between these objects that makes it much more difficult to actually draw a bounding box around the object. Then we need to find a way to predict a bounding box and evaluate our box in terms of how well it does in actually localizing the object within the image. So for this task, the task of object detection, there are a couple of well-known and well-studied benchmarks. The first and oldest is the PASCAL VOC benchmark. It stands for Visual Object Classes. And it's a benchmark that contains around 20 classes, and in total has over 11,000 images, which correspond to over 27,000 bounding box annotations. And it contains also annotations that can be used for segmentation, and we'll see that in the next class. Another benchmark that is more recent, that it was initially developed by Microsoft, and now it's open source, is COCO, which stands for Common Objects in Context. And the main difference with the previous dataset is that it now shows objects in a much smaller portion of the image, along with other objects and a lot of background in the image. So the VOC images were mostly center cropped. So the object was at the center and had a large portion of the image. Whereas in COCO, they're trying to make more realistic data sets. And it's another data set that is used for evaluating object detection. So what exactly do we want to evaluate? we want to evaluate how well a detector does in enclosing the objects with a bounding box. So we assume that someone has spent a lot of time annotating these boxes and drawing the ground truth boxes. So we have our annotated ground truth boxes, which we assume are of good quality. And at test time, we get some predictions from a detector that we are trying to develop. And we want to determine if it closes the object or not. And another assumption is that for any object, we only want to select one prediction. So in this example here, we have some predictions with the ground truths. And essentially for the dog, we have two possible predictions, and we want to decide which one to pick. The question is, how do we decide what is the correct prediction? So to score basically each of these predictions, we use the metric of intersection over union. And basically for each true bounding box, we select the one with the highest overlap. We find this overlap through the intersection over union metric. And as the name suggests, it's the ratio between the intersection, which is the common area between the two boxes, over their combined total area, which is their union. That's why the name intersection over union. So the higher the intersection over union, the better. So that box does a better job. And ideally, we want to have that value close to 1, which means they're perfectly overlapping. In the VOC challenge, a correct prediction is considered when the IOU is over 0.5. So we have a significant overlap between the two boxes. Now that we know which boxes are positive, which enclose the objects, we want to determine what is the overall performance of an object detection system. And for that, we use the metric of mean average precision. We first collect all the bounding boxes. For each one, we determine if it's correct or a false detection. And using, and along with a class that comes with each bounding box, we plot this recall precision curve for each class. So precision is the true positive detections divided by the total detections. And recall is the true positive detections divided by the total positive instances in the dataset. And we basically have a threshold, which ranges from 0 to 1. And we usually pick some of these thresholds every few steps. And for every threshold, we determine the precision and recall value, depending, of course, using the confidence that comes with the class prediction. And for every class, we get these curves. Now, the area under the curve of each for each class is called the average precision. And we take the mean, so the average of those average precision values, and we get the final score for our detector. So looking then at the mean average precision of systems and algorithms that were developed prior to convolutional neural networks in deep learning, we can see that they have topped at around 40% mean average precision. And then possibly also started to saturate. And we will see then with the introduction of convolutional neural networks, how does this affect the resulting performance. But first, it's good to remember what is the typical process of an object detection system. So usually detection is essentially broken down into smaller classification tasks. So we have a sliding window that we slide across the image, and we extract a crop out of these images, and we classify each crop using a classifier like a linear classifier or an SVM. And this procedure, the sliding window procedure, generates thousands of possible candidates, which makes it overall really difficult to account for different ranges of scales and aspect ratios of objects. And it's also very time consuming. In any case, that was a typical approach of a detection system up to a few years ago. And one particular approach that was popular at the time was HOG. So the idea of using histograms of oriented gradients with a classifier. And if you recall, histograms of oriented classifiers are computed based on the gradients and by forming neighboring blocks and finding the histograms along these blocks and creating then one big feature vector. So typically, another thing was that we had to construct a database for the detection task that we had to solve. For example, here we see a lot of examples of p-ball, and which correspond to the positive class, and negative training examples which don't contain the object. And we get this data, we extract relevant features like HOG, and we train a classifier like a support vector machine on this data set. And then typically, once we have, for example, a linear SVM at test time, the SVM weights correspond to a template that we can use to make predictions. We get the input image, we transform it into its HOG representation, and then we we convolve this with the template to get the responses where there are possible objects. So the higher the response, the higher the possibility of object. And we do this for multiple scales of the input image to account for different sizes of the object. In a very similar approach, we can use a convolutional neural network just as any other classifier. So we have our input, we make the image pyramid, we slide the window over the image, each of these images, we extract all the windows, and we classify them with the convolutional neural network. But clearly, this is a very time-consuming process. And if we also consider that CNNs are computationally intensive, this is not the most efficient way of doing it. So advances in deep convolutional neural networks have been accompanied by methods to reduce the number of candidate windows in what is called the region proposal methods, so that we don't have to make all this pyramid with all these images and blindly extract windows in areas where there is possibly no object. And we will explain how it's done. So since people started to use convolutional neural networks and develop detection algorithms using them, if we look at the VOC benchmark, performance has started to go up again. And in fact, we can see that it almost doubled by the previous best methods. So with these results, it's not a coincidence that there has been a rapid progress in the last few years in terms of developing deep learning systems that can be used for object detection. As you see here, basically there are two main branches of research. One is the region proposal methods, and the other is the more regression and classification-based methods. And almost every year or twice a year, you see that we had a new development towards building more efficient systems. And in this lecture, we're going to see some of the most influential, let's say, works in both of these branches of research, starting with region proposal methods. But first, let's just form a more high-level understanding of what are the major differences. So as the name suggests, the region proposal-based methods rely on generating good proposals, good candidate windows that have a high probability of containing an object. So they push all their effort into focusing on the right areas in the image that have an object. And then they use a convolutional neural network to classify each proposal. In this family, we have the methods that are based on RCNN and its future improvements. Single-shot methods, on the other hand, try to aim what the classification pipeline does. So we only want to pass once the image through the convolutional neural network and get all the bounding boxes and detection results at the end. And in this family, we have the YOLO methods and the SSD methods. Generally, YOLO and SSD are faster and possibly less complex to train and implement, while Faster-RCNN and all these methods tend to be more accurate. So let's first consider a simpler case. Let's say that we only have a single object, and in order to extend the classification convolutional neural network, we also want to predict the bounding boxes. Bounding box is usually a set of 4 numbers corresponding to the center of the window that encloses the object and its width and its height. So for this, we can add another head at the end of the network to predict the values in the same way that we do with classification. And we combine these two into one single loss and train the network end to end. Now, the problem is that here it's easy because we know that we have one object, and as a result, we only have 4 coordinates. Generally, in detection systems, we don't know the number of objects in the image, so we can assume that we only have 4 outputs. So the naive idea would be to use the CNN as a classifier, so classifying, doing the image pyramid, extracting windows and classifying all of these windows. But this process is cumbersome, especially for CNNs, and it can create a lot of different crops. And this is where the RCNN family of deep learning methods comes in. So they rely on techniques that find promising regions in the image that have a high chance of containing an object. They extract the features and then classify each of these regions. And there are different variants of RCNN that we will see, and each provides more improvement in terms of speed and accuracy. So what are the region proposals and how do we find them? Region proposals are basically smaller cropped regions in the image that have a blobby shape, like a silhouette, for example. And we can find them by combining together different low-level features like edges or color to give us an indication, like a low-level segmentation. And then we can use a CNN after we extract all these different proposals. We use a CNN to classify each of these proposals. And this is the basic idea that the RCNN family tried to investigate and improve. So RCNN was perhaps the first successful object detection system back in 2015. It relies on a region proposal mechanism to find the meaningful regions in the image that may contain an object. And it uses the CNN to extract features from each of these regions. And now, since we have less proposals than doing exhaustive search, it's more accurate but a slower classifier. So they use an SVM to classify the features extracted by each of these CNNs. So as you can see in the image here, the main idea is we have the image, we have some candidate regions, and through the recognition pipeline that they propose, we end up only with the detections. So RCNN uses a method called the selective search, hierarchical selective search, which aims at generating proposals for classification. So in principle, what it does, it tries to reduce the number of samples compared to the brute force image pyramid search. And it relies on pixel groups to do that share similar characteristics like color, for example, in order to find the object proposals and extract the object regions. So it works by first generating a sort of a segmentation image and many candidate regions. And then greedily, it tries to combine similar regions to form larger and larger regions. And it uses all these generated regions for the next steps for classification. This is an example of the selective search for a region proposal. So it works by first adding, first generating some sub-segmentation mask and extract some region proposals. And then it merges some of these regions together and extracts different set of proposals. And again, it extracts, it connects together the different regions using different similarity metrics and extracts more and more proposals. As you see at the end, the regions that remain are really large, so they have they usually focus on larger groups of objects or larger objects. And by setting the limit on how many of these proposals we want to generate, we can control the complexity and the processing time. Similarly to this, we also have another approach called edge boxes, which instead of relying on pixel segmentation, it uses edges for that purpose. And edges are a natural way of discriminating objects as they provide boundary information for the different regions and objects. And it's generally faster than the selective search approach. So this is an overview of the RCNN algorithm. It first begins by forming this initial segmentation map of regions. And then it groups the different regions together to extract region proposals. So these region proposals could have different size. So what we want to do next is normalize them so that they produce the same output. So we wrap them around a specific size, and then we feed each of these proposals in through a convolutional neural network, and we get the output of the network, so the the final layer, the final dense layer, produces a vector. We get that vector, which corresponds to the features of the of each of the regions, and we classify that through a support vector machine. So it's important to note here that all these arrows that correspond to the different processes happen after we have changed the after we have trained the convolutional neural network. So they happen post hoc, as we say. The RCNN algorithm extracts around 2,000 selective search proposals. As a feature extractor, they used AlexNet. Later versions used different CNNs. AlexNet here was the one pre-trained on ImageNet, and it was then fine-tuned on the PASCAL VOC dataset. They extracted a 4,096 dimensional vector from the CNN, which was then used as an input to the SVM for the classification. And they achieved a mean average precision of over 50%, which was much higher than what was possible by other methods at that time. And this is what sparked a lot of interest in using these systems and further researching how to improve them. Some more details about the RCNN algorithm. The feature vector that we extract is not fed only to one SVM, but in multiple SVMs, because we have multiple classes, and each SVM is responsible either for comparing one with the other class, or the other classes, or comparing between pairs of classes, and at the end we get the majority vote. So it's much more complex in terms of training. Another thing to note is that each of these proposal regions have their some indication on bounding box, because the proposal method crops input for some image input, so they have some indication of bounding box location. And they refine that by passing a vector also through a regressor that gives you the x, y, and height and width of each bounding box. So in that way, they refine basically the output from the region proposal stage. Although RCNN models use pre-trained CNNs to extract the features, the main downside is that they are slow. And they can be slow both during inference but also during training. Slow refers to the fact that we have a lot of different components to work with and train. Since we have to train multiple SVMs, while for every image crop we have to extract the features from the CNN. But the major issue remains the fact that we have a lot of different proposals, thousands of them, and each one has to go through the convolutional neural network. And this results in around over 40 seconds of processing per image. That's for just one image. So in summary, the first iteration of RCNN family was highly accurate and can be used with any deep learning feature extractor. So it's flexible in that respect. And it's also flexible in the sense that we can plug and play different algorithms. So we can use the edge box instead of the selective search. However, it is a challenging system to tune because it's made up of a lot of different submodules. Sometimes it's difficult to tune them. We can tune them independently, but when you put all these things together, it's difficult to make it work as intended. So there are a lot of stages that can have to be done after we train our convolutional neural network. And in general, this increases the training time as well. And of course, during inference, it's quite slow, even if we change the network from AlexNet, for example, to VGG, which is a bit smaller. Then it also does not provide adequate performance. But it succeeded in its original goal in trying to move away from the brute force sliding window approach. So the main problem with the initial RSCNN work is that it needs a lot of time to run each of these proposals through the CNN. So the idea, and then in the next work, is to try and find more speed for the whole pipeline. The idea was to first pass the whole image through a CNN, and then extract regions of proposals directly from the feature map produced by the convolutional neural network. And for every region, we extract a feature vector from the feature map now that has been produced by the CNN, and we can classify that through a CNN or a linear classifier. So the authors proposed Fast-RCNN to fix the problems of RCNN, and the main observation was that that they exploited is that the extracted regions in RCNN have a high degree of overlap. So essentially, they are computing and extracting features, the same features over and over again with the multiple passes of the CNN. So what they wanted to do here is pass the whole image once through the CNN and work from there the rest of the pipeline. An additional advantage is that in this way we can train and update the parameters of the CNN, of the base CNN, at the same time during training. And as you can see in this figure, the trainable parts now are the CNN that does the feature extraction, and as well as the dense layers used for the classification. Notice, however, that the selective search, the region proposal step, is still there. And because it's there, basically now what we have to do is align the regions that are proposed by the selective search with the feature map that we get from the CNN. And this is an overview of how Faster-RCNN works. So Faster-RCNN first passes the whole image into the ConvNet. Then the proposals are generated based on the produced feature map. The extracted features of each region need to be of the same shape. So we again use a method called ROI pooling, region of interest pooling, to make sure that our outputs have the same shape. And we form a feature vector by passing these through a fully convolutional, fully connected layer, and we basically then regress the class and the bounding box of each of these proposals. Let's see now this new element of ROI pooling layer, what it does and why is it useful. So its purpose is to make all the extracted features from the convolutional feature map the same size. So essentially normalize all these crops. And it works by first cropping the region and then resampling it to a fixed size. So in this visualization, we see that example of this process. We have a feature map that is extracted by convolutional neural network. And the selective search predicts the region from this feature map. The ROI pooling layer basically reduces its shape into a specific size using nearest neighbor and max pooling, and then it feeds it into the fully connected layers. Here is a numerical example of how this process works. So given a region, we uniformly cut it into by n block. And for each of these blocks, we extract the maximum value using max pooling. So here we see in different colors the different blocks and that are formed and the corresponding output, so the maximum of that particular block. If the region is not possible to be divided by n by m values, then we essentially just shrink some of the areas so that they have less values to choose from. But the output is constantly the same. Then after the ROI pooling comes the prediction step. In the Fast-RCNN framework, they replaced the support vector machine with a softmax and a linear classifier that produces probabilities for each class. And in this class, we also include one class for the background. So, for example, in the VOC dataset, instead of 20, which is the object classes, we have 21 classes for the output. And prior to the classification, we have some fully connected layers that transform the feature vector, and we at the same time also regress the bounding box location. In this way, the Fast-RCNN algorithm is end-to-end trainable. First, we extract the features, we pull the regions and classify them. Then during the training, we compute the loss function that combines the classification and bounding box prediction. And the gradients then are backpropagated, and the weights for the whole convolutional network are updated rather than doing training in a multi-step approach as in RCNN. So we call this end-to-end trainable because we can do it. We can do the updating of the weights all together in the training. And this is the let's see now the multitask loss that is used by the Fast-RCNN. So Fast-RCNN is an end-to-end learning architecture to learn both the class of the object as well as the bounding box position and size. So the loss encompasses both of these objectives. We have the typical softmax cross entropy loss based on the negative log likelihood, which is the same as the one used for classification. The loss for the bounding box is based on regression, so we do regression to find the coordinates of the objects, and it's called the L1, the smooth L1 loss, and it's essentially combines the squared error loss with the absolute error loss. It behaves like one or the other depending on the different values of the input, and it was empirically found to perform well for this task. This is an example on what intuitively happens when we train for the bounding box regression. We first have the ground truth box. Then the selective search algorithm proposes a box which may have some deviation from the original ground truth. Then our regressor refines that box to match as close as possible the ground truth. So the bounding box regression loss pushes the predictor box towards the ground truth to correct the errors that may have been introduced during the selective search proposal. In summary, Fast-RCNN improves the region proposal approach by reducing the number of times that we use the convolutional neural network. The ROI pooling handles the varying region sizes, so it normalizes the crops that we extract from the feature maps. And in this respect, provides significant speedups. But still, it's a slow process. The selective search, for example, takes 2 seconds. So it's a slow region proposal method. Overall, as we see here, Fast-RCNN is faster, but still the region proposal dominates now the overall computational time. And it's important to note that these speed improvements do not sacrifice the detection accuracy of the Fast-RCNN compared to RCNN. But again, the main thing is that the selective search, it's much slower than the CNN runtime. So in a summary, the Fast-RCNN has 2 main bottlenecks. First, as we saw, the search process is slow still compared to RCNN. And the region proposal step is handcrafted. So we don't take advantage of the training phase to improve it. As a result, we need to have many proposed regions in order to achieve high accuracy. So the logical question is, can we make the region proposal step somehow trainable? And this is, unsurprisingly, the goal of the next iteration of works in the Fast-RCNN line of works, where the goal was to improve the region proposal step. And this brings us to Faster-RCNN. The major innovation compared to the previous work was that it replaces the selective search approach with a region proposal network. So the idea is to use the same CNN to extract the features as before, but also at the same time use those features for proposing regions through another smaller network. This leads to a reduction in the number of proposed regions, while ensuring that the detection process remains precise with the localization. So the rest of the framework remains the same, and we'll focus on the region proposal network. Towards building the region proposal network, they introduced this concept of anchor boxes. These are boxes with predefined aspect ratio and scales, which are essentially used as templates to generate proposals. So in the figures here on the right, first we see the possible anchor boxes that can be predicted across the feature map. And at the bottom, we see an example of some anchor box templates for every location. For one location, which on the top figure is replicated across all locations, since the same templates, the same anchor boxes are used for all feature maps. The region proposal network then that they propose is essentially an additional convolutional layer with a 3x3 kernel. And at each location, this layer predicts a feature vector that is then further processed to generate multiple region proposals using the anchor boxes as reference with different sizes and different aspect ratios. And the location of each convolutional feature map is the center of a box. And they also apply non-maximum suppression on all these regions so that overlapping regions do not, only one box basically survives per overlapping regions. At each of these sliding window locations now, we simultaneously predict multiple region proposals. And the number of maximum proposals for each location is denoted as K, which basically is the number of predefined anchor boxes that we use. So we have we predict 4 times K outputs, 4 for the number of coordinates and K for the number of anchors, and 2 times K for the basically estimating whether the proposal, the region, is an actual object or not. So this is the classification that the region proposal does. So a proposal is labeled as an object if it has a high IOU intersection of a union with the ground truth box, and if the score is over 0.7 for that IOU. Negative labels are assigned to proposals with 0.3 or lower IOU. Once we have determined these labels, then we can train the region proposal network end-to-end with the rest of the system. But it's important to note here that to make the training stable, we want to have a balance between the number of negative and positive proposals in each of these mini patches. And this is the loss function used in the RPN for the RPN, the region proposal network. It's similar as we saw to what we had before. We have a loss for the objects of the objectness of the region and the true box coordinates. Again, regressed using the smooth L1 loss. So putting everything together, we use a single convolutional network to generate the features. The region proposal network or layer to propose regions. We use again ROI pooling in the same fashion as before to extract and normalize these regions, and we classify them through some dense layers. And this can now be done and trained in an end-to-end fashion. So as we saw throughout this journey on the region proposal methods, with every iteration, the authors managed to improve the different aspects of the system. So it's if you see the speed up, the final version or the latest version has over 250x faster than the first RCNN. But still, even at this point, the main drawback is the test time. It's again, the region proposals do take some time, so it's relatively a slow detection pipeline, depending, of course, on the number of proposals, which we can limit, but it will have a negative effect on the detection accuracy. Nevertheless, because these methods are accurate, especially if we have high resolution images, they're preferred in many applications, like, for example, in autonomous vehicles, where it's critical to have high accuracy for safety reasons. Overall, however, the RCNN family has demonstrated very high accuracies compared to what has come before, in even going up to almost double the performance of previous methods. And it's important to see where it all started there. So the RCNN was close to the previous methods, but the various improvements kept pushing the performance even higher. We have Fast-RCNN and Faster-RCNN having a very high score on the VOC. So in summary, in this part of the lecture, we saw the RCNN that introduced the idea of region proposals, Fast-RCNN that unified the CNN backend so that it could be used for the whole image, and the Faster-RCNN that also incorporated the region proposal method. It's important to say at this point that today we can replace any of these components of these sub-modules from the Faster-RCNN framework, for example. We can change the convolutional neural network, and this allows us to further explore the design space and gain more performance. Also, after this works, there has also been some other improvements and modifications. So some works, like the region-based fully convolutional network, made some modification, like removing the fully connected layers to reduce the number of parameters, and added the different mechanisms to make the network fully convolutional, and some improvements towards higher speed.